Welcome back. In the previous lecture, we had seen about nowhere differentiable, space filling curves. In this lecture, we are going to look at nowhere differentiable continuous functions. So we have been, in the past few lectures, we have been studying about continuous functions and the space of continuous functions, the dense subsets, the compact subsets of space of continuous functions. We also extended these density and compactness subsets to LP functions and so on. So in this lecture, we are going to look at example or uh, existence of nowhere differentiable continuous functions. So just to make the connection as a warm-up, uh, we know this result that if a function is differentiable at a point, then the function is also continuous at that point, right? So this basically tells you that every differentiable, uh, I mean, if a function is differentiable at all the points of the domain, then the function is continuous at all the points of the domain, which means that the space of all differentiable functions is a subclass of the space of all continuous functions. A further, as an example, for mod x is a function which is which is not differentiable at 0, and it is an example for which the converse is not true. That is, mod x is a continuous function, but it is not differentiable at every point. Okay, so all differentiable functions are continuous, but all continuous functions need not be differentiable. Examples like mod x and so on. So as we have seen, we have noted that all differentiable functions is a subclass of all continuous functions. A further subclass is the differentiable function such that the derivative is continuous. So Ck is the class of all functions where the kth derivative is also continuous, right? So I mean, a function could be differentiable, but the derivative of the function need not be continuous always. Okay, there are examples for that. So Ck denotes all differentiable functions, all k times differentiable functions, such that the kth derivative is continuous. That's a smaller class than the space of all differentiable functions. And you actually have this nested inclusion, right? And these are all proper subsets. That means you can find a continuous function which is not C1, you can find a C1 which is not C2, and so on. So this lack of differentiability, so in the geometrical term, when differentiability means you are putting a tangent and so on, right? So there is a tangent that exists at that point. So when you don't have differentiability, it basically means there is no tangent, or the tangent is of infinite slope and so on. So the lack of differentiability actually signifies geometrically a edge, I mean a sharp corner at that point of non-differentiability, like what you see in mod x, right? Mod x is not differentiable at 0, and what you have at that point is not a continuous bend, it's like a sharp corner. It comes to 0 from one side and immediately takes a sharp turn to the other side, right? So these sharp corners or these edges are mathematically can be described by non-differentiability. Non-differentiability describes these instances. So the question now comes is there a function which is continuous everywhere but is not differentiable everywhere? So it's nowhere differentiable. Sorry, there is a typo here. Nowhere differentiable. This E should not be. So do we have a function which is continuous everywhere and is nowhere differentiable? That is, it has edges or sharp corners everywhere. Is that possible? And for a long time, it was thought that this is not possible. I mean, if you have a function which is continuous, then the number of points, I mean, the points where it is non-differentiable should be an isolated point. That is how, like mod x, you see, it's differentiable everywhere except at 0. It's an isolated point. So in a neighborhood of that non-differentiable point, the function is differentiable, like in any small neighborhood. So this is how people couldn't think of an example where you have this non-differentiability uh, immediate, like next to each other, like which means that in every neighborhood of the non-differentiable point, there is a point of non-differentiability. Such an example was, so people believe that this is not possible. You don't have a continuous function which is nowhere differentiable. Till actually Weierstrass came and gave an example in 1872. He gave an example of a nowhere differentiable continuous function. His example was this function. Okay, it's a so he wrote it. So he developed this for example as a limit this, of a series of functions. Okay, so sum over these functions. So this is the example that Weierstrass showed, and he actually showed in this example that this is a function which is continuous and it's nowhere differentiable. It's not differentiable at any point of R. Okay, this I've already mentioned that people before that used to believe that this was every continuous function cannot be, I mean, nowhere differentiable is not possible. So then again in 1916, Hardy gave another example of a function which is nowhere differentiable but continuous function. Okay, this again. So this is how things were going. But in this lecture, what we are going to see, we are actually going to see using a bare category theorem that you actually have a large collection of nowhere differentiable continuous functions. Okay, we are not going to construct an example of a nowhere differentiable continuous function. We are going to, we are just going to show that the collection of nowhere differentiable continuous function is non-empty and is actually a big class. Okay, it's bigger than so. Though it is non-intuitive, people couldn't even think of a single example till Weierstrass Hardy came and gave examples. That collection is actually quite a big collection. Okay, that we are going to see in this lecture. So that's the theorem. There exists nowhere differentiable functions in C01. It is a space of all continuous functions on with the domain 0, 1. Okay, so how do we go about the proof? So to start with, we take this set. So you fix a natural number, right, n, and for each n you define this set capital Fn is the set of all continuous functions in C01, right? Set of all functions in C01 such that there is at least one point x such that the supremum of this quotient is less than or equal to n, and this n is what appears here. So you do this for n equal to 1, n equal to 2, and so on. You have f1, f2, so on. So this is basically all continuous functions such that there is at least one point such that supremum of this quotient over h. This is bounded by n. Now the motivation for this definition of the set is that this quotient is what you use in the differentiability of a function, right? Limit of h going to 0 of this quotient is what you define as a derivative. So what we are doing here is that we are saying if I mean all those f such that there is at least one point where this sup is bounded by this n, right? And we can do this for each n. So you have this collection of sets Fn, and you define Y to be the union of these Fn's. Okay. So here in this definition, you should understand when we have to write this definition, when we say f of x plus h, we should choose h such that x plus h is in the domain of f, which is it's in this interval. So when we write this, we basically mean this, that x plus h is always in the domain of, so we only consider those h here, right? Because finally we are going to take limit, h is going to become smaller and smaller. So we only restrict our attention when we take the supremum. It is only for all those h such that x plus h. So once there is an x such that x plus h is in this thing, and over all such h, if you take supremum, this is bounded by n. Y is the union of these fn's. we are going to show that if you have a continuous function which is differentiable even at one point, something like any function, right? Something which is differentiable even at one point, because we want to show that there are nowhere differentiable functions. So suppose f is a function which is differentiable even if it is at one point, then that function should belong to y. Okay, that's what we are first going to show. Suppose we show this, then you can immediately see that any function, any continuous function which is even differentiable at one point will belong to y, which means if you have a continuous function which is nowhere differentiable, okay, they are all outside of y, right? Because they are nowhere differentiable, they are all outside of y. So if this y, which is a subset of C01 by definition here, right? So union of Fn and Fn are a subset of C01. So y is a subset of C01. If y is the entire C01, which means then there is, which means every continuous function is differentiable at some point, right? Anyway, we will see. So we are going to show that f is if f is differentiable even at one point, then such an f should belong to y. So let's start by the definition of differentiability of f. So since if f is differentiable at some point x, then by the definition of differentiability, for every epsilon there is a delta such that something happens. Now we are going to take the epsilon to be 1. So for this epsilon 1 there is a delta such that for all mod h less than delta you have this inequality. This is by the definition of differentiability, right, at the point x. Okay, we know that, right, that by the definition of differentiability, limit of this quotient should converge to f prime of x, which means limit of this difference should go to 0, and we are looking at a delta where such that this quantity is less than 1, less than or equal to 1. So now for all mod h less than or equal to delta, if I look at this quotient, if I add and subtract f prime of x, then by triangle inequality we have this inequality here. On this we have shown that for all mod h less than delta, this is less than 1. So this is 1 plus f prime of x. Okay, so this quantity for all mod h less than or equal to delta is bounded by 1 plus f prime of x. Now for all mod h greater than or equal to delta, if I look at this quantity, now f being a continuous function on the compact sets on the compact set 0 1 on the post interval 0 1, it's a bounded function, right? So this so here the numerator is actually bounded by 2 times the sup norm of f, and the denominator, because mod h is greater than or equal to delta, the mod h is there, so this means 1 over mod h is less than or equal to delta, which is what you have here. So for mod h less than or equal to delta, this quotient is bounded by this quantity here, and for mod h greater than or equal to delta, this quotient is bounded by this, which means if I take supremum over this quotient for all h, right, that is some finite quantity, because it's just bounded by supremum, it's just over these two. Okay, it's basically maximum of these two quantity, right? So it's a finite quantity. So supremum of this is a finite quantity. Okay, so if this is a finite quantity, which means that there is an n such that f belongs to fn contained in y, right? Because the supremum is finite, which means that there is an n such that f belongs to fn, because this is less than or equal to some n we can choose, because this is finite quantity. So if it's less than or equal to some n, then for that n, this f belongs to fn. That's what we have checked here. So from this we get that the f that we started with is in some fn which is actually a subset of y. So we have shown that if f is differentiable even at one point, in this case the point x, then this f belongs to y. Okay. Now we further go ahead and prove that this Fn that we have defined are all closed subsets of C01. Okay, so how are you going to show the closeness? So you take a sequence of functions in Fn which converges to some f in C01. Okay, basically we are taking a Cauchy sequence in Fn, and if we take a Cauchy sequence in Fn, that is also a Cauchy sequence in C01, but C01 is complete, so there is a limit. So you take a sequence fk which converges to f in C01. What we under the supremum norm, what we need to show is that this f also belongs to Fn. If we show that, then we have shown that Fn is closed. So for that, what we do, we by definition, by the fact that each element of the sequence is in Fn, for each k, fk belongs to Fn. So which, now by the definition of Fn, there is some xk corresponding to fk, such that this is valid, right? This is by the definition of capital Fn. This is true. There is an xk. So from this sequence of fk, we actually obtain a sequence of numbers in 0, 1. xk, right? Now this is a compact set, which means this xk sequence is a bounded sequence. So it's a bounded sequence. So by Bolzano-Weierstrass theorem, there is a subsequence which will converge. So let's say the subsequence is so let's say the subsequence is xj and it converges to x0. Okay. Now what we get is that, so because this converges, so xj converges to x0 by the definition of convergence, right? For any h non-zero, there is an n0 such that for all j bigger than n0, mod xj minus x0 is less than mod h. That is this quantity, right? Mod xj minus x0 is less than mod h, which can be written like this as well. This is true for all j in n0. This is by the convergence of xj to x0. Okay, and this choice of n0 depends on the h. Okay, so you have xj less than or equal to x0 plus mod h. So what you do, you choose for each j, you choose hj such that xj plus hj is x0 plus h. This you can do, right? Because xj is some number, x0 is some number, mod h is something that h is again some number that you chose, so it's mod h. So you are looking, so each xj is strictly less than x0 plus mod h, right? So you are looking for an hj such that what is the quantity that you add such that you get x0 plus h. In other words, what we are saying, you are defining hj as x0 plus h minus xj. Okay, that is how you define your hj. So that hj has this property that xj plus hj is x0 plus h. This you can always do. Once you have these three numbers, xj, x0, h, you can define hj with this property. Now by definition, you can see that hj converges to, first of all, this hj is all non-zero. That is following from here, because it's strictly less than. So this is hj, you have to add a non-zero quantity to reach this number. Okay, now that is true for all j bigger than or equal to n0. So hj is non-zero because this inequality is valid for this condition that j is bigger than or equal to n0. Okay, so now so by definition we have hj converging to h, right? Because xj converges to x0. So by the definition of hj, if xj converges to x0, then hj should converge to h. Okay, so this also we have. Now what we do, we are going to look at this point, because finally what we need to show is the following, right? We started with the sequence fk, we have a limit f, we want to show that this f is also in fn. So if you have to show f is in fn, that means that f should satisfy a condition like this for some element of the so some element of this interval 0 1. So we have found an element x naught in 0 1. Okay, we have found an element x naught in 0 1. So we what we do is that we are going to show that this f satisfies this condition for at the point x naught. Okay, if we show that, then that f will automatically belong to fn. That's our aim. So to show that f satisfies this condition at x naught, we need to consider what is f of x naught plus h minus f of x naught over h, right? So that's what we are doing here, f of x naught plus h minus f of x naught. So if we take this, then I add and subtract these two quantities, that is fj xj plus hj and fj xj. So that is subtracted here, added here, subtracted here, and then by triangle inequality, I have these three terms, right? Now, if you look here, in these three terms, the first term, whenever j is bigger than or equal to n naught, by our definition, we had seen that. So this first term, x naught plus h minus fj xj plus hj, which is this term here. So this first term is here. This becomes this. Basically, I am replacing x naught plus h by xj plus hj, because that is how we chose hj. Hj was chosen such that this sum is same as this sum. So I can replace this sum with this sum. This I can do for all j greater than or equal to n naught. That's what we have done here. And this remains same. Now, so this is equal to this. Now here you see it's the same argument, that is xj plus hj, xj plus hj, it's f minus fj. So this quantity is less than or equal to fj and f, right? This quantity is less than or equal to fjf, which means, and this is converging to 0 as j goes to infinity, right? Because fj converges to f. So this quantity as j goes to infinity will go to 0. The first term here. Now look at the second term. The second term is fj xj minus f of x naught. What we do is we add and subtract f of xj. So we have fj xj minus f of xj plus f of xj minus f of x naught less than or equal to. So I have added and subtracted, applied triangle inequality. Now this term here, the arguments are same like the previous case. This is less than or equal to norm fj minus f, which goes to 0. Okay, and this term remains as such. Now this again, f is continuous function. We are seeing that xj is a sequence converging to x naught. So continuity will preserve this convergence. So f of xj will converge to f of x naught. So this also, as j goes to infinity, goes to 0. So as j goes to infinity, this term goes to 0, this term goes to 0, this term goes to 0. So basically, as j goes to infinity, this term goes to 0, this term goes to 0. Okay, so in this, if I take limit of j going to infinity, see in this side there is no j dependence at all. So the first two terms are going to go to 0. So basically, as j goes to infinity, what we have is this term is less than or equal to something, this term here. So in other words, the idea here is that if I start with f of x naught plus h minus f of x naught over h, which is this term divided by h, this is what we need to show, right? We need to look at this and say that supremum over h of this is less than n. Now this quantity, by whatever we have done here, is actually equal to limit of j going to infinity, numerator this, denominator this, which is fine, right? Because as j goes to infinity, hj converges to h. So the denominator here is will converge to the denominator here, the sequence of numbers. The numerator again is a limit of this quantity here, and that's what we have shown here, because this quantity is what we have here. Okay, so as the limit of j goes to infinity, you have that this quantity is limit of this, but this again I have some miswriting here. This here, part of this was valid for j bigger than or equal to n naught, but when we say that j goes to infinity after some finite stage, j will become bigger than n naught. So this is perfectly valid. So this is for j bigger than n naught, and this, because we have assumed that fj is in fn, this is actually less than or equal to n, which means this is less than or equal to n for every h, right? So if I take supremum over that, you still have that property, which means that we have shown that this f little f belongs to capital Fn, which means Fn is closed. So we have shown two things now. That one is that every differentiable function, and any function that is differentiable at a point should belong to the capital Y set, and the capital Fn sets are all closed for all n. So now we will show that these sets also has empty interior. Okay, Fn's are empty interior. So to show that it's an empty interior, which means that if I take any element of Fn, right, and if I take any ball, every ball, every epsilon ball centered at F, it should intersect the complement of Fn, right, which means I should be able to obtain a function in the complement of Fn such that the distance between them, I mean, they lie in the epsilon ball, right. So this is what we need to show. So given F, to show that it has empty interior, I need to obtain a G in the complement of Fn such that the distance is between them is less than epsilon. So to do that, what we are going to do is the following. By the Weierstrass approximation theorem, okay, by the Weierstrass approximation theorem, there is a polynomial P such that f of f minus p is less than or equal to epsilon by 2. This is like you have seen that every continuous function can be approximated by polynomials, right? So given this epsilon, I can find a polynomial such that f minus p is less than or equal to epsilon by 2, right? There's no issue here. We have done this already in the course. Okay. So now this is one property which I want to highlight because this is what we are going to use crucially to construct this G here. Okay. So what is this? This basically says that if you have this is true for any polynomial. If you have a polynomial, and this is now the polynomial in the closed interval 0, 1, right? So the derivative of the polynomial, supremum of the p prime in 0, 1 will be finite. That is the slope. So the slope of the polynomial at every point, if you take supremum over that should be finite. Okay, on this compact set, it cannot blow up. Okay, this is very important. When you say supremum, which means that the slope, that's a tangent at each point of the polynomial cannot slowly does not slowly convert, kind of go to infinity. Okay, this is a property of the polynomial. This is true for any polynomial when you restrict it to the compact set 0, 1. Okay, so using this fact, we are going to use this. So what we are going to do, we are going to approximate this polynomial p by a piecewise affine function, okay, g, and that will be the g that we want. Okay, and that g, we are going to do it. So what I can explain here how I'm going to whatever I'm saying here is this. Let's see if I can draw something. Okay, so what I'm saying, suppose say you have a polynomial p. Suppose say this is your p. Okay, this is your polynomial p that you have obtained from the Weierstrass approximation theorem. Now you want to approximate it by a g, and the distance between g and p should be epsilon by 2. So let's say we put a epsilon. So I'm not using a different colors here. So let's say I'm going to, so this is the epsilon by 2 distance, okay, of this polynomial p. Okay, I have epsilon by 2 distance polynomial p. Okay, now this is the graph of the p that you have in 0, 1 interval. Okay, so this point, if you look at, is actually the point 0 comma p0. So p0 has a value, it could be 0 or non-zero, whatever it is. So 0 comma p0 is a point on the graph, which is the starting point here, right? Because 0 is the first point. So this is the starting point here. Now what you do from here, now you taken, so this distance that you have taken is the epsilon by 2 distance. Okay, this is epsilon by Okay, this is epsilon by 2 distance, this is epsilon by 2 distance here, right? So you take that. Now we are going to construct a piecewise affine function. How are we going to do this? So we are going to construct it such that the slope of the function that you construct is bigger than n, because finally you want g which is not in Fn, right? If you want g which is not in Fn, that means supremum over that quotient should be bigger than n, and that's quotient is nothing but the quotient that appears in the definition of derivative. So we are going to choose, we are going to construct a g such that its slope, that is its derivative at every point where it is differentiable. So because as you said, we are going to construct a g, right, which is outside Fn, but it's a continuous function, right? We don't, so it may not be differentiable everywhere, right? Just a continuous function. So we are going to consider a continuous function which has a slope wherever it is differentiable, its slope is bigger than or equal to n, right? So I'm going to show it here pictorially. So this is something which you can approximate with any point here, and the fact that this p prime is finite, that is the norm of the p prime is finite, is can helps you choose such a g such that g prime is bigger than n, because it is not going to go, because this p is going to be, the slope of the thing is going to be bounded, of the polynomial is going to be bounded. So what you do here, you start with this 0 comma p0 here, okay, from here, sorry, okay, I am moving something else, I don't want to move that, I want to draw something, okay. Okay, so what I do from here, at the point 0 comma 0, I draw a line of slope bigger than n, okay, and then I come back with another, again a slope of bigger than n. You see the mod of g prime is bigger than n, which means the slope can be n, should be bigger than n, and so this is again the mod of the slope will be bigger than n. So you choose, so you keep, now this is, you keep doing this, you keep constructing this function. Now this function is not differentiable, you see, it's not differentiable at every point. For instance, this function is not differentiable here and all these edges. So all these looks like mod x point of point at edges, right? In every other place it is differentiable, it's like a linear function, right? Piecewise, that's why I said piecewise affine function. It's like a straight line, and this is differentiable at every point here, and in these points the derivative will be bigger than n, because that is how we are going to draw. We are going to draw a line such that the slope is bigger than n for each of these lines, each of these piecewise line, the slope is bigger than n, okay. So we keep drawing this, so this will be, sorry, it's not becoming straight line, anyway you get the point, right? So what I'm saying, if you do this, so this whatever we have drawn, that zigzag line is an approximation, and approximation of this p, and the distance between this, so this function g, so this is your g, okay, this is your g, and so this g minus p is less than or equal to epsilon by 2, okay, because that is how we chose, because we had started with an epsilon by 2 and so on, right? Right, so that's how we draw this. So this way we obtain a g, and the claim is this g is going to do whatever job which is does already, you see. So you have chosen a g. Now this g is a continuous function, okay, it's a continuous function. So you have a continuous function, it cannot belong to Fn, it cannot belong to Fn, because that is how you chose your g such that g prime of x is bigger than n for all. So there are points where it's not differentiable, it is fine, where there we don't, that this doesn't even make sense. Wherever this makes sense, then this is bigger than n, which means there is no point x in the domain such that g prime of x is less than n. So that's how we consider. So this g is a continuous function, not in Fn, so this g belongs to this, and this g satisfies this, because if you apply the same triangle inequality, so f minus p and g plus g minus f, add and subtract p here, then that you see is that is less than epsilon, okay. So that is how you construct this. So from this we have shown that Fn has empty interior. So Fn is a closed subset and also empty interior, which means Y is a countable union of closed sets with empty interior, like with a countable union of nowhere dense sets, right? Okay, so now this G satisfies the requirement. So Fn has empty interior for all n. Okay, so if Fn has, so every Fn for each n, Fn has empty interior. Okay, I forgot to, yeah, I don't need to draw anymore. So uh, if Fn has an empty interior for all n, then interior of Y, which is the countable union of all Fn, should also have empty interior. Okay, so interior of Y is also empty. Now by Bayes category theorem, since C0 is a complete metric space, complete Banach space, this and Y is a count, Y cannot be equal to C01, because if Y is equal to C01, which means that C01 is a countable union of nowhere dense sets, right? No, that's not possible by Bayes category theorem, which means that this should be a proper subset, which means that if it's a proper subset, that means the complement of Y is a non-empty set. Okay, and what is complement of Y? Complement of Y is precisely the collection of all nowhere differentiable continuous functions, right? Because if you have a function which is even differentiable at one point, we have already shown that belongs to Y. So the complement of Y should be the collection of all nowhere differentiable continuous functions. So that's a non-empty set. So we have shown the existence of nowhere differentiable functions. In fact, we have even shown much better. What we have shown is that if I take a function which is which is in Y, which means it is different, which means supremum of that is less than or equal to n for some n, right? And if you take an epsilon, then you can actually approximate this f by a nowhere differentiable continuous function, right? What I'm saying is that every continuous function which is differentiable even at one point, it can be actually obtained as a uniform limit of a sequence of nowhere differentiable functions. That's what this is saying here, because this is a function which is differentiable even at least at one point, right? F belongs to Y, so F belongs to one of the Fn's, at least one of the Fn's. So there is a point of differentiability of F. So F is a function. Now what we have shown here by this thing, by the non-empty interior and so on. So you, for every a such F, you can get a G which is nowhere differentiable, that norm Fg is less than or equal to epsilon. Okay, so in fact the class of all nowhere differentiable function is so large that in fact every differentiable function can be actually obtained as a uniform limit of nowhere differentiable functions. Okay, that's what we need to prove in this result, what we need to prove in this lecture. So we will see in the next lecture. Thanks a lot.